So now we're going to try to find the maximum power extraction that we can get with a wind turbine. And we know that the power extraction can be written as 1/4 rho AT V1 plus V2 times V1 squared minus V2 squared. And we showed that if we could design a turbine that stopped the wind so that V2 is equal to 0, we could get 1/4 rho AT V1 cubed power out of this. But we'd like to know if that's actually the best we can do or whether there's some other way to get even more power. If you fix all the things that are generally fixed, that is the incoming wind speed you can't change, you can't change the incoming density of the air, and you could change the size of your turbine, but let's assume we're trying to get the maximum power for a specific turbine. So we'll fix the size of the turbine as well. And if you do that, you can see that the power extraction is a function, you can be thought of as a function of the one and only variable, which is V2. And you're going to control V2 by the design of your turbine. So you're going to control it by the type of blade you have, by the angle of those blades, etc. The speed with which how easy it is to rotate your blades. All those things will affect your V2. So we're going to assume that you have control over V2. And if you did have control over V2, what would be the best value of V2 to set it so that you get the maximum amount of power? That's the plan. Well, if it's a function of V2, here it is. Well, how do you find maxima? Happily, you're all engineers, which means you're very good at calculus. And so we know that the way you find maxima and minima is you take derivatives. You take a derivative, and then you set that derivative equal to 0, and that will find you a maximum or a minimum. So to find P max, we take dP dV2, because that's our variable, and set it equal to 0. That's what we're going to do. We're going to take the derivative with respect to V2 and set it equal to 0. So here's my function. Take that derivative. You should all practice taking that derivative. Go ahead and do it. I will take the derivative, and we'll see how if we agree. So dP dV2 equals, well, 1/4 rho AT. Those are constants out in front, so I don't need to touch those. Now I'm into land where I have to take some actual derivatives. So we've got V1 and V2. Well, V1 is a constant, so that just drops away. The derivative of V2 with respect to V2, that's just 1. So then I have V1 squared minus V2 squared. Of course, I'm going to use the product rule here. And then I take the derivative of this one. So I have V1 plus V2, not touching this one, and take the derivative of that one. Derivative of V1 squared, of course, is still just 0. Derivative of negative V2 squared is negative 2V2. So there's my derivative. I'm going to clean that up a little bit. 1/4 rho AT. I'm going to write that as V1 squared minus V2 squared minus 2V1 V2 minus 2V2 squared. So that's just multiplying this through. Minus 2V1 minus 2V2 squared. I get this stuff. Then I'm going to add all the V2 squared terms. So I get dP dV2 is equal to 1/4 rho AT. I've got V2 squared here and another 2V2 squared there. So I got minus 3 V2 squareds. Then I've got only one term with just a V2 in it, V1, V2. And then I've got plus V1 squared. That looks good. So that's my derivative so far. I'm going to set that equal to 0 because that's how I find the maximum. So let's see how that goes. Set it equal to 0. So I have 0 on the left, 1/4 rho AT. I keep writing 1/2. 1/4 rho AT minus 3 V2 squared minus 2V1 V2 plus V1 squared. I can divide by 1/4 rho AT because that's divide by the other side. 0 divided by something is just 0, so I get rid of that. So, and I'm going to move these things over to the other side too because I don't like having all these minus signs. So divide by this, get rid of it, and move stuff over. So I got 3V2 squared minus 2V1 V2 plus V1 squared. And that's all equal to 0. Oops, I messed up. plus minus. So I'll write it again. 3v2 squared, moving this over, plus 2v1 v2 minus v1 squared equals 0. All right, so that looks fine. Then what? Well, I'm going to try to factor this. This is a quadratic equation in my unknown. My unknown is v2, so I'm looking for the solution to v2. v1 is a constant, so this is a quadratic equation. I've got v2 squared, v2, and then nothing. So this is classic quadratic equation. I can factor it. I get 3v2 minus v1 times v2 plus v1 equals 0. So make sure that works. 3v2 times v2 gives me 3v2 squared. That looks good. 3v2 times v1 gives me 3v2 v1 minus v2 v1. That gives me 2v2 v1. That's correct. And v1 times negative v1 gives me negative v1 squared. So that is the correct factorization. The solution to this equation, therefore, is v2 could either equal, if it equals negative v1, that's a possibility. That would set this equal to 0. Or 3v2 could equal v1. Those are the two things that would make that go to 0. This is impossible. So that's not a real physical solution where the air reverses course after it hits your turbine and goes back the way it came. That's not going to happen. That's absurd. So that's out. That's not a valid solution. But this one's okay. This says that the maximum occurs when your velocity at your outlet is your velocity at your inlet divided by 3. So if I want maximum for P max, so if I want maximum solution here, if I want the maximum amount of power, this is the velocity that I want to achieve for the outlet velocity. I want to design my turbine so that the outlet wake velocity is equal to 1/3 of the inlet wind speed. That's going to give me my maximum. I should worry a little that that's a max, not a minimum. I mean, it could conceivably be a minimum instead of a maximum. I know it's not really a minimum. How could I know that? Well, let's see. If I made V2 infinity, for instance, this would go to something really, really massive. Go to something massive and negative, though. So I guess, yeah, so it would go massive and negative. So that would be the minimum. If V2 went to infinity, it would go to negative infinity. So that's not possible. So this has to be a maximum because it's an interior, an interior extrema, and the maximum occurs sort of at V2 equals, the minimum occurs at V2 equals basically infinity. So this is the solution. That's the velocity I want. But now I need to figure out what that leads to in terms of maximum power extraction. So I'm going to go back to my power equation. My power equation, I've now said P max is equal to 1/4 rho AT V1 plus V2 times V1 squared minus V2 squared. And this will be maximum when V2 is equal to V1 over 3. So I just plug that in. So I get that the maximum maximum power generation, 1/4 rho AT V1 plus 1/3 V1 times V1 squared minus 1/3 V1 all squared. That's my maximum power when I have this optimum velocity for V2. So P max is equal to 1/4 rho area swept by the turbine. This is obviously just 4/3 of V1. And this thing is going to be 1/9. So that's going to be 8/9 of V1 squared. Because I'm going to subtract 1/9 of V1 squared. 1 minus 1/9 is going to give me 8/9. And when I multiply all that together, I get P max is equal to 32 over 108 rho AT V1 cubed. So I just multiplied 1/4 times 4/3 times 8/9. And finally, I can clean that up a little bit. That does simplify if you divide everything by 4 to 8 over 27 times rho AT V1 cubed. So that is your maximum power that your turbine can possibly get. The best possible turbine can extract this amount of energy from the wind. So if you're given a certain wind speed, you can calculate the maximum possible power that any wind turbine could extract from that wind.